Hey there, let's get into something that often strikes fear in the hearts of many students and teachers for that matter, the Lagrange error bound. It sounds really scary, but it's actually not as bad as it sounds or looks. So let's go. So basically, Brooke Taylor, the guy that came up with Taylor polynomials, right? Like he named them after himself. That's pretty sweet, or maybe someone else did. Came up with a theorem that basically says, my polynomials are great for approximating values, but don't trust me unless I can give you an error, right? Like I could give you, Mr. Groden, could give you approximations for anything. I could say, hey, the length between here and, I don't know, something that you're looking at in your room is approximately 10 feet away. And you could be like, how does he know that? And I could say, well, I don't have any reason to know how far I'm off by. Well, then how good is my measurement if we don't know how close I am? So Taylor said that. He's like, well, okay, let me give you a theorem for how much my polynomials will be off by. Now, we can never actually prove the exact amount of error that we're off by. That would mean that finding the error wouldn't matter. We would just find the exact value every time. So he sets out and he basically says, all right, here's what we know about error. Error is the true value of something minus the approximated value. And we take the absolute value of that because we don't know if we're off by a positive amount or a negative amount. Error is just a positive amount. So imagine like I measure myself to be 6 feet tall. That's my approximation, that's my measurement. And the true value of me is like, let's say 5 foot 11 inches. Then the error is 1 inch. Right? We subtract the two values to get the remaining amount that we were off by. So sometimes the error is known as the remainder. So you'll sometimes see R sub and a value instead of just error. So Taylor proved that the exact error of any of his polynomials is equal to the absolute value of the function, the actual function that we're approximating with a Taylor polynomial p. So if you subtract f at whatever value we're approximating at minus the approximation function, take the absolute value of that, that would give you the true error, right? That's like the true value minus the approximation value. He proves that it's essentially equal to the first unused term in his polynomial. So we would take the n plus first derivative. If you went out to the fourth derivative, you'd use the fifth derivative over the n plus 1 factorial. And there's the z number we'll get back to in a second. X minus c, x being the value you're approximating at, c being where you're centered about, like normal, all raised to the n plus 1. So if we went out to, like I said, the sixth term, the sixth degree, we'd use the seventh derivative, 7 factorial. This would be to the 7th power. X again is the value we're approximating at. C is the center, what we're approximating the function about. And z, what is that? Z is some value that must fall between x and c. It will fall. It could be equal to one of those, but it must fall somewhere inclusive between x and c. He proves this. We're not going to go through the proof. It's one of those things where you're actually going to have to trust me on it. I'm sorry. It's probably one of the only times I don't explain why out of all the thousands of videos I've made. So z is going to fall somewhere in between x and c. Think about it as the first ignored term. That's it. So Lagrange comes along. I think his first name was Joseph. We'll call him Joey Lagrange. Maybe it wasn't Joseph, but it's definitely Lagrange. He comes along and he basically says, well, here's Taylor's theorem. Taylor says the exact error, the exact amount we're off by is this. But we can never find the true value of z. Remember, it's some x value that happens between what we're centered about and where we're approximating. So Lagrange comes along and says, well, we can't find what z is. So I'm instead going to say that the error bound, the highest error that could happen, is the maximum value of the derivative found between c and x. So that's the only thing that we don't know, right? Go back to Taylor's theorem. We don't know what this derivative is going to be. We can calculate this every time. We can calculate that every time. But what we can't calculate is that z value. So he says, fine, z falls between x and c. That's what Taylor proves. So I'm going to just find between c and x what the highest value that this could be. And that would make for the highest possible error, which is great because we don't really care what the exact error is. We just want to know how close are we. We're within an inch or less, like with my measuring analogy. And we take absolute values of everything that needs absolute valuetizing so that our error is a positive number. It's the first ignored term, right? Remember that your general term of a Taylor polynomial is just this. So don't be as scared about this as it might first look. It's basically this with a little bit of alteration here and some absolute values. It's just the n plus first term. All right, let's put it to action. You'll see that it's not as bad as you might think. And then we'll rock some more exercises in video 3 in this lesson. It says use a second degree Taylor polynomial about x equals 0 to approximate e to the negative 1. Okay, well we know e to the x about 0 is equal to 1 plus x squared over 2 factorial, and I'll go out to another term, x cubed over 3 factorial plus dot 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 x to the n over n factorial. Now we just want to use the second degree Taylor, so that'd be these first 3 non-zero terms. So that means that e to the minus 1 is approximately 1 plus negative 1, I'm going to write it like that, plus negative 1 squared all over 2 factorial. That's our approximation. It says use the Lagrange error bound to find the maximum error for the above approximation. So the error is going to be the absolute value of e to the minus 1. That's f of minus 1. You're basically saying, here's the exact value, minus our Taylor polynomial approximation. So I'm going to put all of that in here. 1 plus a negative 1 plus a negative 1 squared all over 2 factorial. Now, if you're keeping score at home, when you simplify all this, 1 plus a negative 1 is 0. Negative 1 squared is 1 over 2 factorial is 2. That's 1/2. So the difference between this and this is approximately, right? Well, it's going to be the exact error, but the true error, is going to be less than or equal to the maximum value that we get between the two values where we're centered and where x is. Now, depending on which is greater, they could flip roles. So in this case, x is negative 1. That's where we're approximating. That's less than or equal to that z value, which is less than or equal to 0. 0 is where we're centered about. That's it. So it's the max value of the derivative. We take the absolute value because it's the error of the n plus first term. Now we were told to go out to the second degree, so that was the nth term. So the n plus first term would be the third derivative. And that's evaluated at that x value, z. You could also put an x here and an x there. That's fine. Times the absolute value of x minus c. Well, x again is negative 1 minus where we're centered about is 0 raised to the third power. Right? That's the n plus first term. That's all over n plus 1 factorial, which is 3 factorial. So that's going to be equal to, and we kind of simplify this down. Let's think about this. What's the third derivative? Well, f triple prime of x is super easy to find. That's e to the x. Right? E to the x's derivative keeps being e to the x. And so what's the maximum value? So the max value of e to the x on negative 1 is less than or equal to x is less than or equal to 0. Well, let's think about that. E to the x is a graph that looks like that. It's forever increasing. So the highest value that e to the x is going to be at 0. You don't have to go through this and prove that the absolute maximum happens at 0. You just need to have the correct value. So that would be, I'm not going to write an arrow there. Let me get rid of that thing. That would be e to the 0, which is 1. So all of this is 1. You have to do a little bit of logic to say this is the highest value that the third derivative will be on this interval. That's it. So that's 1 times negative 1 minus 0. The absolute value of that is 1 cubed is 1 all over 3 factorial, which is equal to 1/6. That's the Lagrange error bound. So what that means is the difference between e to the negative 1, which is 1 over e, and essentially 1/2 is at most going to be 1/6. That's it. That's the furthest that our approximation is going to be off from here. And if you want a little bit better error, do more terms and figure out what that bound of error is going to be using the Lagrange error bound. Not so bad. Now, before we leave off, I want to show you graphically what just happened here. So you're not like, wait, what did we just do aside from a process? So I've drawn out a couple pictures here. This is the zoomed out version. Here's p sub 2 of x. So this is the approximation. So this is 1 plus x squared over 2 factorial zoomed out. And this is e to the x right here. That curve is e to the x. You see that they're very close to each other over this interval. In fact, here's our value here at negative 1. So I zoomed in a little bit closer. Here's our value at negative 1. This is the polynomial's approximation at negative 1. We see it's right at 1/2, right? And this is e to the negative 1. We see it's a little bit lower than 1/2. What we just found is we just didn't figure out the exact difference. That's the true error. We said that this distance right here is less than or equal to 1/6. That width is at most 1/6, the amount that the approximation is off from the actual. Isn't that beautiful? I think it's awesome. So the Lagrange error bound, it's really about knowing your Taylor polynomial general term, doing the next term, the n plus first term, and then understanding that you have to maximize that n plus first derivative on the interval between where you're centered, in this case we're centered at 0, and where we're approximating, in this case that was at -1. That's it. I'll see you in the next video. Until then, peace.